Okay, so for the rest of the class, we're going to talk about explosive eruptions, which are pretty cool. Up to this point, most of our classification that I show here is based on explosive products. So we're actually going to talk about the eruptions themselves. How do you produce an explosion? Why does it explode? Sort of the parts of the volcano and how they interact with one another. So when an explosion happens, magma essentially breaks and is blown out all over the countryside. It disperses. And what drives the process is gas, either gases that were contained in the magma or mixing with external water, which could be groundwater, could be ocean water, could be some sort of lake water, whatever. I don't like the terms, but we use them a lot. When the gases come from within the magma, we call it dry. It's really not, because most of that gas is water. I don't like the term, but it just means no external water. And then wet eruptions are also called phreatomagmatic, because you got the magma component. Phreatic means atmospheric derived water, ocean water, river water, rainwater, groundwater, etc. When a volcano erupts, it usually produces one or more of the following: pyroclastic fall deposits, which is stuff that falls out of the eruption column; pyroclastic flow deposits, which are gravity-driven avalanches of the explosive stuff that comes out of volcano; and then surge deposits, which they're a little bit like a pyroclastic flow, except they're really dilute. The clouds are not very dense, so they don't hug the topography quite as well. They're sort of gravity-driven, but sometimes they can hop over topographic barriers. They're kind of a mix between gravity-driven and atmospheric-driven. So they kind of have a mind of their own. All three can be deadly. Pyroclastic flows are the deadliest. You get stuck in a pyroclastic flow, you're done. You're not surviving it. Some people have survived surges, but not many. And pyroclastic fall, people survive, but some people die. You get hit with a big block, that can ruin your day and your life. So those are the things we're going to cover further. Okay, this little diagram here sort of summarizes everything that we're going to talk about in the next few slides. And in the next slide, I'll blow it up a little bigger, but it basically includes all the parts of the process. And I think the easiest way to look at this diagram is to start at the bottom. All right, so below this line right here, called the exsolution surface, there is enough pressure to keep all the gases in solution. All the gases are dissolved in the magma. If you remember back to your test, I had that question: if the water content is 4.8% and the solubility is 4.9%, where are the gases? Well, the gases are still dissolved in the melt. So below this, there's enough pressure to keep all of those volatiles dissolved in the melt. There's no bubbles. But as you rise up in the column, there's less and less pressure, right? And at some point, that changes the solubility. And where you see this exsolution surface, that's where the solubility and the concentration are the same. And bubbles now start to form. So what you have are bubbles forming above this exsolution surface. Below that, there's too much pressure. All the volatiles stay dissolved. Above this, the concentration exceeds the solubility and you start to form bubbles. As you go higher up, there's less pressure. So as you move up from the surface, the pressure gets less and less. If there's less pressure, what does that do to bubbles? They can grow, and there can be more of them. And that's what this diagram is starting to show, is as you rise up, the size and the number of bubbles increases to the point where you hit this next surface, which is called the fragmentation surface. And we believe that somewhere around 77% bubbles, the magma gets weak enough to start breaking apart. At that point, it's inflated to a foam, basically. You guys have seen pumice, right? That's the state of the magma at this fragmentation surface. Is that highly inflated? It's more pore space than it is magma at that point. And those bubble walls are really thin, and they're real fragile, and they start breaking. And all that gas then wants to do what? Wants to go up, right? And it starts pulling the various pieces with it. Those pieces now are starting to break up. So that's called the fragmentation surface. And it occurs when we get about 77% bubbles. So the various parts are first, we have exsolution of water and other volatiles at that exsolution surface. That's where we get bubbles to form. These bubbles rise. As they rise, they experience less pressure. They're able to rise faster. That increases the magmastatic pressure because stuff is highly buoyant. It wants to move up. When it hits about 77% bubbles, now the bubble walls are so thin that they're easily broken. The gases are able to then escape from the bubbles and start carrying this broken material upward. And then as we move up in the chamber, there's less and less pressure, restricting movement, so the stuff starts moving faster and faster and faster. And at some point, it can move from subsonic to supersonic speeds in excess of 700 miles an hour. And then, depending on just how big of a conduit, how much gas is coming out, lots of different factors, you're going to end up with an eruption column that is blasted by gas up into the atmosphere. Now, at the same time, this is a really highly idealized diagram. What you're not seeing is that the walls of this conduit are actually broken. This is rock in a volcano. So there's lots of little breaks for gases to escape. And what can happen is sometimes it can actually lose enough gas, especially before it hits this fragmentation surface, that the gases are able to bleed off. And sometimes they never fragment at all. Enough gas escapes so you can actually prevent a volcanic explosion. And this is a really powerful sort of system. I mean, we've got stuff moving at supersonic speeds in a conduit, lots of earthquakes. And what happens a lot of times is you get a lot more breaks in your conduit, which can bleed off more gases. So what has happened sometimes is you can start out with an explosive eruption, but because it's so powerful and it breaks up its conduit, it can bleed off enough gas to make a transition from an explosive eruption to a lava flow. Probably a lava dome producing eruption. So again, you've got your exsolution surface. Below that, too much pressure for bubbles. Above that, volatiles come out of solution and form bubbles. They rise up. It gets more and more inflated, turns to a foam. When it hits about 77% bubbles, it starts to break at the fragmentation surface. Those gases then jet upward, carrying the broken pieces. The closer it gets to the surface, the less confining pressure there is, the faster it moves. Eventually, it can change from subsonic speeds to supersonic speeds, and you can get really tall eruption columns forming this way. At the same time, you might have a situation where the conduit starts to break up from all this activity and lose gas, and then can actually shut off the explosion and turn it from an explosive eruption into an effusive eruption. So there's a lot going on. Lots of different chemistry things going on, lots of different physics things going on. This is why we make you take chemistry and physics sometimes in the same semester. So again, here's the fragmentation surface. Here's this diagram that's blown up a little more. Occurs somewhere around 75, 77%. And the important thing to remember is that stuff here is magma, right? This is melted rock with bubbles. What you're doing actually is breaking a liquid. People don't think much of breaking a liquid. When we think of breaking things, we think of breaking solids, right? Snapping elastic substances. You can break liquids if the strain rate's high enough. Basically what happens when you shake up a soda bottle, pull the top off, stuff sprays all over, you get little droplets that are flying every which way, right? You separated those droplets from the body of liquid with the high gas. It actually physically broke apart. Now each little droplet is a liquid, right? And in this case, each little pumice fragment is probably still liquid while it's in this conduit. It's still hot enough that it's still very deformable, but it's being broken apart at the same time. So it's a weird situation where it's breaking like a solid, but it's still technically a liquid, and yet it's flowing on gas. So it's a really weird system with all sorts of different components going on at the same time. So you can just sort of envision this accelerating mass of broken liquid that's inflated to a foam. It's a foamy liquid that's broken apart and it's jetting up. Once it leaves the vent and is exposed to the atmosphere, it's going to cool off really quick and turn into those big solid pumice fragments that then can fall back to Earth. Or if the eruption's super energetic, those pumice fragments are going to collide together up through the conduit and then in this sort of roiling, boiling cloud that goes up. And those big pumice fragments then get broken down smaller and smaller and smaller because the pumice walls are so fine, and you can end up with this really super fine ash when it started out as a foam down around that fragmentation surface. So it goes from a foam to pumice to ash as it moves up. And you got to think of this stuff moving at 600, 700, 800 miles an hour up through this conduit. So it's a really odd system. Explosions are really neat, especially from a science standpoint, because it's chemistry, it's physics, it's, in this case, geology, sort of all mixed together. You got to understand all of it to really have a mental model of what's going on. Now, this is a little bit interesting, too, is that the level of those surfaces do not remain stagnant during an eruption. And the reason is that if you look at everything above the fragmentation surface, right? Is it mostly air or is it mostly magma? Is it mostly gas or mostly magma? It is, because remember, it's inflated to at least 77%, and now it's breaking up even more. Before it erupted, what was in that conduit? It was actually probably rock that had this eruption sort of reams out a pathway. So it was rock sitting over the magma chamber. Now it's mostly gas sitting over the magma chamber, right? What does that do to the pressure? Lowers it. So what should that do to that exsolution surface? Exsolution surface is, remember, the pressure. It'll move it down because now you have less material sitting above it. So over time, that exsolution surface moves farther into the chamber. So bubbles start growing at depths where they didn't before. The fragmentation surface does the same, and that can actually migrate way, way down. And then if it starts bleeding cast, those things will migrate back up. And it'll sort of, if the fragmentation surface rises so much that it comes out of the volcano, do you have an explosion? No, then it's a foam that comes out on the surface. And some people believe that obsidian lava flows are actually collapsed foams. They come out as a foam, and as they flow across the surface, they just collapse into this dense gas. So they go from almost being a pumice to being dense. And you can look at these glassy lava flows out in California. The ones I showed you had obsidian in it. The tops of them are all pumiceous, like a pumice, but it's actually lava. You can see the old foam sitting up there. really wild, weird stuff. That's why I like this sport, because it kind of, you really got to use your imagination, because this stuff is not something it's easy to observe out in nature. In fact, you can't observe this out in nature. So these migrate down. This is kind of the key statement right here. These surfaces migrate down because there's less pressure over the top as this stuff erupts. I talked about if we bleed off gases during eruption, we can change the location of those surfaces. We actually know this happens. There's seismic signals that are indicative of gas loss. You can measure how much gas remains in the magma in the samples you get on the surface. Basically, you take samples and you crush them up, you heat them at a really high temperature, and you drive off the gas. You can measure it. That's what I did for my master's and PhD. I took lava samples and crushed them up, heated them up to 1,000 degrees, and was able to see how much gas came off. Basically, almost nothing. The water contents were like 0.1%, and we know deep down they were probably 5 or 6%. So it lost a lot of gas as it erupted. Some people have looked at hornblende, which is a hydrous mineral, and if it degasses, if the material around it gasses too much, it becomes unstable and actually breaks down. So you can look at these reaction rims on hornblende crystals and see that they're experiencing some sort of disequilibrium with respect to the water content surrounding them. So we know this stuff degasses while it's erupting. Okay, so now the fun part. So when you break up all this material at the fragmentation surface and eject it from a volcano, it can take on several forms. So if it's blasted straight up as a vertical column and falls back to Earth, we call that pyroclastic fall. Now, if there was no wind, you should have sort of a bullseye kind of pattern of isopachs around your volcano, right? Stuff goes up, comes back down. But we always have winds. So you're going to get, when we go back to the Walker diagram, you're going to get that axis of dispersal. It looks like a bunch of superimposed ovals. And they can be big, they can be small, depending on the strength of the eruption. So these things are wind driven. What happens is they're jetted up. And then once they get up in the upper atmosphere, they can even rise buoyantly because the ash column is hot. But then at some point, they butt up against the stratosphere. They spread out, anvil-shaped cloud, not all that different from what an atomic bomb looks like. And then the material can fall back to Earth. And the plume is basically wind-driven once it gets up above the volcano. If the material falls back to Earth and flows across the surface, then we have a laterally moving system that we call pyroclastic flows and pyroclastic surges, where most of the movement is downhill and gravity-driven. Pyroclastic flows are the dense bottom part, and the surges tend to be the finer, more dilute ash clouds that sit above sort of this rolling avalanche. These are, so I'm using the term flow, right? But it's a flow of particles. In this case, it's a flow of ash or a flow of broken material. If you go inside a pyroclastic flow, it's solid rock chunks that are banging against each other. It's not a liquid, right? It's not a gas, right? But it's moving as a mass, and it's moving as a liquid would move. And if you think of a liquid, it's just molecules that can move relative to one another. In this case, it's rock chunks that can move relative to one another. So as a mass, we call it a flow. We actually use fluid dynamic models to quantify its movement, even though the actual pieces inside are solid. So, no, it's a great question. It's like you're calling this a flow, but it's actually solid chunks of rock. Yep, it's exactly what it is. Avalanches, sometimes we call these debris flows, where it's loose debris on the Earth's surface. It's rolling downhill. It's all solid chunks of rocks and trees or snow or whatever. But if you look at it, it's following the topography, moving just like a dilute fluid would, right? So yeah, we call these flows, even though they're chunks of solid stuff. It's a great question. Okay, we're going to look a little closely at each of these. Just get started and then continue this next week. Each of these different types of pyroclastic activity leads to different types of deposits. So the pyroclastic fall deposits look different than pyroclastic flow and different than pyroclastic surge. And when you go out and look at these deposits on the landscape, you can usually tell which is which. Sometimes they can be a little confusing, but for the most part, pretty easy to figure out which is which. Pyroclastic fall, the material that's falling out of these tall eruption columns, tend to mantle the topography. They're about the same thickness everywhere. So if you look on top of a ridge, it's the same on the side of a hill, same as at the bottom. Really different than a pyroclastic flow, which is going to travel down the lowest parts of the topography. So these things drape or mantle the topography. And you see this wind-driven axis of dispersion with the isopachs. These tend to be well sorted. If you remember back to physical geology, sorting means the consistency of particle size. What that means basically, if you dig through an ash deposit that's somewhere, all of the ash is going to be about the same size. Close to the vent, it's all going to be big pumice pieces. Move a few miles away, it might be baby head size pumice pieces. Move 5 miles away, maybe it's just pea size pumice pieces. And then once you get many miles away, it's just going to be ash. So at each location, it's going to be really consistent in size. That's really different than an avalanche. When an avalanche comes to rest, the big come to rest, the small stuff comes to rest. If you look at the deposit, it's got big chunks, little chunks, medium-sized chunks, all mixed together, very poorly sorted. These things can vary in thickness a lot. Some airfall deposits, some pyroclastic fall deposits are 1,000 meters, kilometer thick, where you've had big ultraplinian events. Sometimes it might be a small Sturzian or a small strombolian blast and just leave a couple millimeters of ash across the landscape. Usually when this stuff hits the ground, it's no longer hot. So when you get hit by pumice that's falling out of the sky, it'll be warm, but it's not 1,000 degrees C and going to eat a hole through you. You know, it's no fun getting hit by pumice, but it's not probably going to burn you at the same time because it's had so much time in the atmosphere to cool off. So these pyroclastic fall deposits, the biggest thing is that they mantle the topography and they are well sorted. Those two things tend to separate them out from the other deposits that we'll see. So I showed you a little diagram a minute ago of what's going on below the volcano's vent. This is showing what goes on above the volcano's vent. And there's 3 parts to an eruption column. The lower part is what we call the gas thrust area. It's down here. That's where the upward movement is due to gases pushing the material upward. But at some point, the gas being emitted from the volcano isn't going to be enough to keep it moving upward. Now, at that point, stuff should fall back to Earth, but it doesn't. The reason it doesn't is because all the gases that are there are really hot. surrounded by cold air. So this is hot. What does hot air want to do when it's surrounded by cold air? Wants to rise, and it will rise. And what it does is it rises all the way to the base of the stratosphere. What happens in the stratosphere, here in the lower regions, we call the troposphere, what happens to the temperature as you go up? It gets colder. In the stratosphere, it does the opposite. So at this level, you got cold air rising, or you got warm air rising, but then it starts hitting warmer air. And at some point, you're going to have the same density, and you'll get no more rise. So what it does then is that the wind just blows it right at that level. And that's where you get that anvil or umbrella shape. That's that stuff sort of sitting beneath the stratosphere because the stratosphere is too warm for it to continue to convectively rise. And then as it moves outward, the biggest stuff is going to fall close. Medium stuff's going to fall a little farther out. By the time you're way out, you're just going to get really fine material. And it lands over the whole landscape. It doesn't land preferentially in the river valleys. Just as much will land on top of a ridge as at the bottom. So that's why it mantles the topography. And you get these really nice isopack maps. Isopleth is a measure of average grain size. So that should decrease as you move up, just like the isopacks will decrease as you move up. So what's kind of cool about all this is that volcanoes are fun to watch and interesting to see, but they leave behind really great deposits for doing field work. I love doing field work on older volcanoes. Everybody thinks, volcanoes, you want to watch them erupt because that's the cool part. Actually, going out and seeing volcanic deposits and measuring them is really fun and interesting. I like the old volcanoes as much as I like the active ones. So there you go. This is Chile from just a couple of years ago, and it really shows the different parts of the eruption cloud well. So you can see up to this point right here that the column is really tight and constrained. That's being driven by gas. And at this point, from let's say maybe here to there, now this is just being driven by density. This is hot, this is cold, so this moves up. And then up here is the stratosphere. You get equal density between the ash column and the overriding air, and it just sort of fans out, and you can see the primary wind direction is this way. So then what will happen is big stuff will fall here, medium stuff will fall here, finest material will fall out there.
Does that help for the depth too? Like say the bigger items are on the bottom.
Yeah, more stuff will fall close. Yeah. Because only the fine ash can sort of stay up in the atmosphere very long. Anything that's this big, it's going to come down. It's going to eventually come down. And the bigger it is and the more dense it is, the quicker it comes down. So yeah, you'll get really thick deposits here, and the size of the clast and the thickness will decay as you move out. So here, and this is a great diagram because you can sort of see the relationship between the eruption itself and the deposits that are going to be underneath. This just sort of illustrates the temperature. As you move up in the troposphere, you can see that the temperature decreases, but then in the stratosphere, it actually starts increasing again. And then we don't really, for volcanic work, we don't worry too much about this. These are the two areas right here. This is 50 kilometers, so that's 31 miles up into the sky. You can get volcanic eruptions that go that high, but typically not. Sometimes the ultrafiltration can go way up in there. Yeah. It's unusual, but it can happen. It can just blast through all those zones. All right, I think I'm going to stop there and hand back your test quick if you